Welcome. This is the first in a series of presentations designed to provide guidance on technical aspects of the indicator methodology. And in this session we look specifically at monitoring program design and the requirements of a program that can provide sufficient data for SDG indicator 632 reporting. And to accompany this presentation there is a technical document which is available on the SDG 632 support platform. And just to say that this presentation focuses on surface waters because there is a separate presentation specifically for groundwaters. So efforts to collect monitoring data for indicator 632 should provide sufficient information on the current ambient water quality status, but it should also be at the national scale, and it should enable long-term trends in water quality to be identified. So to be able to identify these trends, you need data for the 5 core parameter groups. You need data from sites across the country, and measurements should be taken in a standardized and consistent manner. So this presentation provides guidance for countries to help meet those reporting requirements, and it focuses on monitoring program design that makes best use of available resources. So there are 5 main steps of the indicator methodology. The first is to define the RBDs, or the reporting basin districts, and then to define the water bodies, to define the monitoring locations, to collect the water quality data, and then use those data to assess or to classify water quality for each of those water bodies. So monitoring program design is presented here within the context of these 5 steps. So RBDs, or reporting basin districts, these provide the sub-national reporting units to disaggregate the national indicator score. So countries report the national score, but these can be broken down by these hydrological units. So in this example shown here, the country has been divided into 3 reporting basin districts. And then each reporting basin district has been further subdivided into, in this case, river water bodies. So each river water body here is either a tributary of the river or a small section of river between 2 tributaries. The next stage is to define the monitoring network, and this includes defining the monitoring stations, and then using the data collected from these monitoring stations, the water bodies are then classified as either good or not good. A useful tool to help conceptualize the monitoring program process is the monitoring program cycle, and this can be summarized into 3 main phases. The first is the design phase, second, implementation, and the third is the assessment and reporting and management phase. And this approach is useful for designing any type of water quality monitoring program, not just for indicator 632 reporting. So the first stage is to set objectives, and the success of any monitoring program is dependent on having clearly defined objectives. So this can only be done when a monitoring program team have identified the information that is needed to support the water quality management, and the data that need to be collected to provide the information and the reasons behind their selection have been defined. And for indicator 632, this has already been done. It's to provide long-term trend monitoring data for the 5 core parameters in as many water bodies as possible using the resources available, and to provide the most extensive and reliable data possible for the classification of ambient water quality. The next step in the cycle is the preliminary surveys. Now these help to fill knowledge gaps in the study area, to inform monitoring program design, and for example they may help to determine the natural variability in the quality in water quality at a given site. So all available information from any other studies or monitoring programs in the same or similar geographical areas, or using any data from similar monitoring techniques may be useful. So for example, historical water quality measurements, any hydrological data, any biological data, and information on the geology and land use. Site investigations such as sampling might be needed before you can finalise your monitoring programme. These will help to see how homogeneous a particular site is within, how water quality varies across a site, for example. For example, maybe across a river, the water quality may not be consistent, so there may be some preliminary surveys needed to define exactly where best to do the monitoring. And also just to check that any identified or potential monitoring sites are easy and safe to access, and we're not introducing any potential risks to field staff. So the next stage is the actual monitoring network design, and good monitoring network design makes efficient use of all the resources while still producing high quality data that allow the objectives of the monitoring program to be met. So there are three main activities involved in monitoring network design. The first is to select the monitoring media and the sampling and analysis methods. The second is the actual monitoring location, and the third is to define the sampling frequency. So if we focus first on the monitoring media, in this case, indicator 632 is only concerned with the physical and chemical properties of water when we're reporting at level 1. And the parameter groups to fulfill level 1 reporting have already been prescribed by the methodology. But within each of these parameter groups, the country can decide which specific parameter to use for reporting. So this decision may be based on methods currently used already, or the capacity and resources available to initiate a new program. The method that is used for each parameter should be decided at this phase, in the design phase. So not just which parameter will be measured, but the actual specific analytical method, how that's going to be undertaken, whether it's going to be done in the field or if the samples are going to be collected and transported back to a laboratory. And also at this stage, consideration should be given to the limits of detection of the chosen method. Some methods, for example, may not be able to get down to low enough concentrations to be of use. So it may be necessary to check and make sure that the methods proposed are capable of attaining those low concentrations. In some cases, it may not be possible to transport the samples from very remote monitoring stations back to a laboratory within a recommended time frame. So each analysis has a recommended holding time where the sample can be held for before analysis. So therefore, in those cases, it may be better to do a in situ analysis using one of the field methods available. So there are field methods available for all of the core parameter groups, but countries may decide that the facilities of a purpose-built analytical laboratory, which have improved levels of accuracy and precision, are preferable. This is especially relevant for the nutrients and nitrogen and phosphorus, especially if we're looking to get down to very low concentrations. Dissolved oxygen, for example, can be fixed in the field and analysed in the lab, but the most common method is to use a dissolved oxygen probe in the field. So the next stage is to select the monitoring locations. So it's important to make clear the difference between monitoring locations and monitoring stations. So monitoring locations are the general area where a sample is to be taken from, such as a section of a river or a geographical coordinate for on a lake, whereas the monitoring station is much more specific. And this is the detail on exactly where the samples are to be collected or the analyses are to be performed. So, for example, a monitoring location on a lake may be defined by a geographical coordinate, but at this single location, there may be several monitoring stations. And as shown here, each of these stations may be at a different depth. And when selecting monitoring locations, a general rule to make sure that that defined water body is classified accurately is to assume that the more heterogeneous a water body is, the more monitoring stations are needed to be able to classify it reliably. So if more than one station is needed per river water body, they should be located at both impacted and unimpacted locations. If they are just one type, so if all the monitoring stations are unimpacted locations, that may then result in a classification which is not doesn't reflect the true reality of that water body. But where resources restrict monitoring to a single location for a water body, the optimum location is at the most downstream point, where the river water body drains into the next designated water body, which may be another river section or a lake. This location, the lowest point within that river system, will integrate all of the influences on water quality arising from the catchment upstream of that location. So still talking about rivers, the criteria used in this example shown in this figure, so at least one monitoring location per water body. Also a consideration here was the road network. So each of the monitoring locations is at an intersection between a river and a road, so it makes it easier to access. So that feeds into the next criterion, which is that access is safe, and if there is an intersection between a river and a road, there's normally a bridge, so you can sample in this case directly from the bridge. Another consideration was to make use of any hydrological data which is being collected in the area. So monitoring stations were co-located with any hydrometeorological stations. None of the monitoring locations were close to known point sources of pollution. So, for example, any effluent pipes from sewage treatment plants or from any industrial activities within the catchment. And also, they are representative of, as I said in the previous slide, impacted and unimpacted catchment areas. Moving on to lakes, selecting monitoring stations for lakes. The number and locations of monitoring stations in lakes depends on the size of the lake and also its morphology. So if a lake is small and well mixed, one sampling location near the centre or at the deepest part of the lake may be adequate. If a lake has multiple basins, a monitoring location may be required within each basin. A large single basin lake, 4 monitoring locations, 1 in each sector, may be adequate. And if lakes, for example, are arranged along a river course, having a monitoring location in each one would be needed. So for the purposes of SDG Indicator 632, lake monitoring locations should, the same as for rivers, always be away from known inputs of pollution. and samples from lakes that stratify seasonally should always be taken at a fixed depth below the surface, but this site should be above the thermocline. So alternatively, an integrated depth sample can be collected. So this kind of sample can be achieved by taking discrete depth samples and mixing them at the time of sampling, or using a hosepipe sampler. So the next stage is choosing the sample frequency, or how often the samples are collected. So trend monitoring, so to be able to define trends over time, requires a long-term record of relatively consistent data for the same places and at the same frequency for a number of years. So ideally, samples should not be collected during extreme events, such as during flooding or when discharge is very high, unless this is a regular seasonal occurrence. The samples should be taken during comparable conditions at the same times and locations over consecutive years. And ideally, simultaneous discharge measurements can assist in the interpretation of water quality data at a later date. The frequency of data collection can range widely. In certain circumstances, continuous measurement may be possible through an automated instrument, but the other extreme could be annual grab samples. The sampling frequency should be higher at locations where water quality varies to a greater degree than at stations where water quality is relatively consistent. This means that if it's known that the water quality doesn't vary that much, that water quality can be represented by fewer monitoring events. The recommended frequency is at least one sample per season, but if resources allow, it's recommended to sample once a month, but preferably no less than 4 times each year. Sampling at these intervals every year will provide information for long-term trend monitoring, which is applicable for SDG Indicator 632. When looking at lakes, again, information on the variability of lake water quality should be used to inform the sampling frequency. So locations where water quality varies should be sampled, again, more frequently than where it's relatively consistent. Seasonal variations should be taken into account, and whether the lake stratifies, and also the residence time of water in the lake is also important. Does the water sit in the lake for a long period, or is there a constant flow through the lake? Collection of hydrological data should accompany the collection of water quality data if possible. For rivers, for example, this may be as simple as collecting information on the water level, the flow volume, or estimating flow volume, or the velocity at the time. This is because the concentrations measured of some water quality parameters can be heavily influenced by the hydrological conditions at the time of sampling for that particular water body. So conditions can change over time depending on the weather, the season, or natural anthropogenic alterations to the water body. So therefore, hydrological measurements made at the same time and at the same location, when the sample's taken, the water quality sample's taken, this can help assist in interpreting data at a later time. For example, you might see outliers in the data which may correspond to spikes in the hydrograph for a river or something, which may explain them. Field operations comprise a significant component of any water quality monitoring program budget. So field work and data collection should follow standard operating procedures, SOPs, to help ensure consistency and reliability. And also, whilst in the field, any observations made during the sampling campaign may prove useful retrospectively to help interpret the resultant data. Field notes should be carefully taken. These should include the date and time of sample collection, weather conditions, sample ID, notes on any field measurements taken, and those preservation methods used for samples which are going to be analysed in the laboratory. Additional observations might include notes on the aquatic flora, any unexpected smells or colour in the water, and the potential presence of sources of contamination, such as a broken pipe or evidence of livestock that may have entered the water body. Health and safety should be of utmost importance for any fieldwork campaign. Sampling locations should be designed to be safe to access during the design phase, but this needs to be checked during each campaign to make sure that nothing's changed and samples can be collected still safely and should be free from hazards. The appropriate personal protective equipment should always be made available. It should be brought and used during any sampling campaign. And a first aid kit should always be taken along just for any minor emergencies. Efforts to avoid working alone should be taken, but when avoidable, strict call-in times and response plans should be put in place. Quality assurance, or QA, is the management system used to maintain a desired level of quality in any service. And for water quality programs, this is no different. With adequate QA, the data will be credible and defensible, and it can be relied upon to assess the water quality, and therefore any management actions based on the data can be done reliably so. So you can obtain credible data by using recognised or standard methods, such as those from ISO, the International Organisation for Standardisation, and by following good laboratory practice as prescribed in ISO 17025. And within a QA plan for a monitoring program, there should be SOPs for all activities, so including the sampling, calibration, analytical processes, and the audit of each of those. Quality control is different from QA. The quality control consists of the actual series of technical activities that aim to evaluate and improve the quality of data. QC helps to reduce the possibility of error being introduced into results, and this is relevant for all aspects of the implementation phase, right from the collection, the preservation, transportation, storage, analysis, data handling, and reporting. Data management is a key aspect of any monitoring program. The data storage system should allow the relevant data to be extracted for analysis and classification of water bodies easily. For example, if stored correctly, it should be straightforward to extract the data for a particular time period or for a particular RBD. So investing time and effort into managing data appropriately adds value to the data for the future and ensures they remain valid beyond the planned lifetime of the monitoring program. So water quality data can go through many processes and are manipulated by many people. So this results in lots of opportunities for errors to be introduced. For example, incorrect measurements or units or conversions, limits of detection may be recorded incorrectly. The number of significant figures could differ between one person and the next. And any errors here should be detected before the data are stored or reported. A centralised storage system should be backed up regularly. The central data repository should keep all relevant metadata associated with the water quality measurements. So that includes the geographical information, the monitoring type, the water body, and any other recorded notes. These should all be stored together. So in summary, knowing where water quality is good and where it is not is essential if countries are to implement management decisions for its improvement. So good monitoring program design is critical in this process. and ensures programs deliver sufficient and reliable data that are capable of tracking improvements in ambient water quality over time. So just lastly, this presentation provided information for ambient water quality monitoring program design, particularly in the context of implementation of SDG indicator 632. Reporting basin districts and water bodies should be delineated and defined before a monitoring program can be designed. The monitoring program design flowchart summarizes the essential steps, and these 3 phases help to produce and maintain a successful water quality monitoring program. And consistent quality assurance and periodic re-evaluation of the monitoring program can help to ensure the program is capable of supplying sufficient and reliable data for indicator reporting. So that just leaves to say thank you for listening, and this final slide shows the link to the SDG indicator support platform and the email address for the help desk.